So now that we have the idea of dimension to work with, we're going to consider certain vector spaces that we associate to a matrix. There are three of these vector spaces that we're going to discuss. The first one is called the null space. And for each one of these three vector spaces, we're going to be able to not only define what the vector space is, but also we're going to be able to compute the dimension. It's going to turn out that there is a very interesting collection of relationships between the dimensions of these various spaces. So first one, null space. The null space of a matrix is an old familiar idea. It's the set of homogeneous solutions. This is really a very old idea. We saw this back in chapter 1, collection of homogeneous solutions. And one might ask, well, then why do we need to rename this as the null space? Well, what we've seen very recently that this set of homogeneous solutions is in fact more than just a set. It's a special kind of set. It is a vector space. So the term null space has the feature that it emphasizes the vector space structure of this object. And also is a little bit more compact to say null space than to say vector space of homogeneous solutions. Okay. All right, so we already know how to find the null space. We already know how to find homogeneous solutions. That is, you row reduce the matrix, solve for your pivot variables in terms of your free variables. Old news from early in chapter 1. What we don't already know, or what we don't already realize that we know, is how to find a basis for the null space. And it turns out that our existing method not only gives us the null space, but it gives us a basis for the null space. So an easy, quick example of this is to consider a matrix A, and I'm going to presume that we already have it reduced down into reduced row echelon form. Of course, that's just a row reduction, and let's suppose that the reduced row echelon form is this. Right. So we solve for the pivot variables in terms of the free variables, and that gives us this. And this is where we stopped in chapter 1. The observation I'll make here is that you can factor out the y, turn that into this, and we realize that this is saying that every homogeneous solution is a scalar multiple of that one vector. Said differently, this one vector is a basis for our null space, because every vector in the null space is in the span, is a linear combination of, which in the case of one vector, of course, just means a scalar multiple of this one vector. Okay, well, that's a silly, quick example. Now let's see a more interesting one, and that is consider a matrix A that row reduces down to this. Now here, when you solve for your pivot variables in terms of your free variables, you get this. And again, this is where we would have stopped in chapter 1. We have a complete collection of all of the homogeneous solutions here. Again, observe that we can separate this into chunks and factor out the variables and rewrite this as that. Well, now we have all of the homogeneous solutions written as the span of a pair of vectors. So this is a new point of view on this, this collection of homogeneous solutions. Now, that means that our collection of homogeneous solutions is a vector space. How do I find a basis for this vector space? Well, it turns out that these vectors themselves are a basis. How do I know that that's a basis? Well, it's quite clear that that collection of vectors spans the homogeneous solutions. And that's the observation we just made. The looming question is, how do I know that this pair of vectors is independent? How do I know that that list is independent? Well, let's make this observation. This is what we would have to ask. This is the algebra we would have to consider if we wanted to decide if this pair of vectors is independent. I would need to know, is there a linear combination of these vectors? Is there a linear combination of them that adds up to 0? Well, in fact, this linear combination that I have to consider is exactly the same as this linear combination that I'm already considering. Said differently then, I need to know, how can there be a y and w that makes that equal to that? And looking at it that way, I see it's very clear that y has to be 0 and w also has to be 0. So, said differently, the only relation between these vectors is the trivial relation where these are both 0. And that means that these vectors are independent. So this is always going to work. Related to this is this theorem that the dimension of the null space is always equal to the number of free variables. We're not going to write down a rigorous, complete proof of this in this course, but the idea is exactly what we just saw in the example that we just looked at. Specifically, you get a basis vector, one for each free variable, and therefore the number of vectors in a basis, namely the dimension, is equal to the number of free variables.